Hello, so I'm Alex Fowler. I'm based at the University of Otago in Dunedin, New Zealand, and I'm going to be chairing the next session. So first up, we have Sherry Zhang. Sherry is a PhD student in the Department of Econometrics and Business Statistics at Monash. Her research focuses on computational statistics and visualization, and her presentation is 15 minutes, so there'll be time for live questions at the end, and is about a package called Cubble that is used for working with spatio-temporal data. So I now hand over to Sherry.
Thanks, Alex. Can everyone see my slides and hear me well? Yeah. Okay, cool. I will start. So minimize here. So hi everyone. Today I will be talking about switching between space and time, spatial temporal analysis with Cubble. So just a heads up, it will be a computational talk. It's mainly centered in R. You will expect to see a lot of code. First, a little bit about myself. I'm a third-year PhD student at Monash University in Melbourne, Australia, and my research centers on exploring multivariate spatial temporal data with data wrangling and visualization tools. And if you are interested in my work and know about other things I'm doing, here's my contact details. So here's my Twitter, GitHub, and also my website that you can find more information about myself. Often, spatial temporal data are stored separately, and this is convenient for data collection, but not necessarily for analysis. And joining the spatial and temporal data into a long table is not necessarily the best way to structure the data. This is because of the inefficient memory use due to the repeated information, especially when large geometrical objects are combined with frequent temporal data. For example, if you use R, you potentially know about a package called SF, and they store the the feature geometries in a geometrical column. And if the feature geometry is large, and on the temporal side, you have daily or weekly data, and when you cross-join those two together, you will have a very large joint data set, and it is not efficient to operate in that way. So this motivates me to think about how to rearrange spatial temporal data for analysis. Ideally, we would like a data structure that can easily pivot in between spatial and temporal form. It will be a plus if the interface is a table or data frame, the most common data structure in R, so that we can use the functionality from existing packages for spatial and temporal analysis. So today I will be introducing a new data structure called Cubble for vector spatial temporal data. So for spatial temporal data, there's vector, there's raster, there's trajectory, and today we will be only focusing on vector data. And a Cubble has two forms, which you will see shortly that we can pivot back and forth between the forms. So on the left, you have the nested form. So all the spatial variables are in columns, and temporal variables are all nested out in a list column called TS. And in the long form on the right, the time series data are shown in columns, for example, the T1, T2, and date. And each row is cross-identified by the site, the station, and also the date in the long table. So you can see for each row, they have a unique combination of ID and date. With Cubble, you can easily pivot in between these two forms in the analysis. And in general, spatial operations will be performed in the nested form on the left, and temporal operations are carried out in the long form on the right. And the pair phase spatial and phase temporal are used to switch the form between each other. With phase spatial, the focus of the data is now on the temporal form after the switch. And this is corresponding to the long form. So you are essentially switched from the nested form on the left towards the long form on the right. And with phase spatial, the long Cubble is switched back into the nested form, and you will be facing or operating on the nested form. So here is a syntax comparison with and without Cubble. So the right-hand side probably easier to look at. You can on the right-hand side with the Kabul code, you can do some spatial analysis in the nested form, which is the form of the CB object. So CB object, you pipe that into your spatial analysis. You can do some spatial analysis, and then you switch with the phase temporal, and then you do some temporal analysis, and then you can switch back to do some spatial analysis again. So sometimes these spatial analysis include extracting some interesting sites. For example, on the left, I have highlights a few codes for you to look at. These are the codes where you have to pull out a few interesting IDs and then filter on the temporal sheet about those interesting IDs. So in Kabul, these updates are automatically handled by the phase spatial and phase temporal. So you don't actually need to manually update your spatial and temporal data to match with each other. And also the Kabul pipeline chains all the operations together. So there's no intermediate objects that's created in the workflow. So essentially you will not have your own SPID, TS subsets that's floating around in your workspace to confuse you. So now let's see Kabul in a data set of Australian weather stations. So the stations data on the left records 30 weather stations, along with their longitude, latitude, elevation, and name. And on the temporal side, we have precipitation, maximum temperature, minimum temperature. These are all collected on a daily basis for each of the 30 stations in 2020. So here I have the map and the time series plot to show you the extent and where the locations are. So to cast two separate tables in a Kabul, you can supply them in a nested list, as I have highlighted here. So you supply them as a list with the name spatial for the spatial data sets, temporal for the temporal data sets. You also need to tell Kabul some identifiers it looks for. The keys argument is the spatial identifier, the ID. Index argument is the temporal identifier that prescribe the timestamp. The coords argument is used to specify the coordinates. And here you see the results after we have cast the data into a Kabul. And from the Kabul header here, you could read a few information. So the key is ID, as it's shown here. There are 30 different IDs, and it is in the nested form. And on the third row, you can see here, it shows you the temporal variable along with its type. So it should not surprise you that we have date, which is a datetime object. The precipitation, Tmax, and Tmin, these are all doubles. So you can see here, it's reflected in the form variables here. So because there's some missings with some stations, so not necessarily all the stations have the same number of observation in the temporal side. So it does not really matter. We can store different number of rows for each in each listed column. And also, if you happen to have an SF object or a civil object you want to pass into a Kabul, that's also fine. So there will also be reflected. There will be like a small indicator here to show if the spatial data is an SF object or if the temporal data is a civil object. So here is what the Kabul looks like when it's being switched between the long form and the nested form. So with the weather object we just created, we can turn it into the long form with the function phase temporal. So we have weather and we pipe it into phase temporal, and then that gives us a data set called weather long. And you can see here that it now changed to show it is a long form. And then on the third side, it starts to show the spatial variables that we have. So it's the lat, long, elevation, name, and WMO IDs. And now here, in the main form, in the main table, you have the precipitation, Tmax, and Tmin that's showing up here. And on the right-hand side, the weather long can be switched back into the nested form with the function phase spatial. So as you can see here, like from the last line of code, phase spatial and phase temporal are the exact inverse. So that gives us the exact same objects of weather back and weather. So they're exactly the same. So it's the exact inverse. Sometimes you might need to access variables from the other form of your analysis. For example, we may want to calculate some per station summary of this time series data. We can refer to the temporal variables in the nested form with the $sign. And here I'm calculating the average maximum temperature across the whole year for each station. And I need to get access to the Tmax from the list column TS. So what I do here is that I refer to the column as TS $Tmax. And that would create a new column called average Tmax, which do the averaging. And in the long form, you need the couple verb unfold to move the spatial variables into the long form. And here I use the unfold to move the longitude and latitude into the long form, so they shows up. And this will create a repetition unless you specify the unfold to move the variable here. And the purpose of me moving the longitude and longitude here is that later I will show you how this can help us to create the glyph, to create a visualization called glyph map. Sometimes, although we technically have spatial and spatial temporal data, we might choose to fix a few stations to explore their temporal pattern, or select a few timestamps to explore their spatial distributions. A more holistic approach is to explore the space and time simultaneously. And now I will show you an example of how to use Kabul to explore temporal patterns across space in a glyph map. So the glyph map is essentially a transformation of temporal variables into space. I have a short illustration here to show you how the transformation works. So here in 1 shows a single stations on the map with its longitude and latitude. And 2 is its associated timestamp, associated time series data. In step 3 on the bottom right, the temporal axis is transformed into spatial scales with linear algebra. And once we have the time series being transformed into that, in the transformed axis, they can be placed on the map as in 4. So to make a glyph map, you can use the geom_glyph function from the Kabul package. It requires a pair of major and a pair of minor variables as required aesthetic. The major variables are the spatial coordinates, longitude and latitude here, and the minor variables are the temporal coordinates, date and Tmax here. And here I'm showing you a full example of using glyph map to explore Australian weather pattern. The code here on the left has 3 blocks. And in the first block, we create a Kabul object from the stations and TS data that we have. So you should have already seen this code. And in the second block involved wrangling the data using the nested in the long form. So sampling 20 stations is a spatial operation. So it is performed in the nested form. Then we need to do a summary of the average maximum temperature by month. It is a temporal operation, so the Kabul is switched to the long form with phase temporal. The glyph map requires both the spatial and temporal axis as aesthetic, so we move the column long and lat with unfold into the long form. And the last chunk here shows the ggplot code to make the glyph map with geom_glyph. So you have geom_sf here to make the underlying map, and then the geom_glyph to do the little glyphs, the U curve, temperature curve on the map. And then there's some aesthetic, some curves, some other things you can change within the ggplot code to make it on the right. So on the map, you can see that the temperature curve in the north and south are relatively constant throughout the year. For example, the ones on Tasmania Islands here and the one here. And also those inline stations, for example, in the Eastern Australia, like those, they are having a much visible variation in the year as comparing to the coastline ones. So we are here in Australia and we know our temperature curve is the U shape. So this is the U shape, and probably you won't see that U shape very clear in the northern and southern here. But with the inland side, it's pretty clear there's a U shape or like a happy face shape within the temperature. So this wraps up my talk today. Kabul has already been on CRAN, and there's a recent release that I'm submitting yesterday. So it still goes through the CRAN process. There has been, yeah, that's the version update. And if you're interested in the slides, there's the link that you can put it in your browser, and then you can see the slides on your own space. And there's the GitHub reference there's the reference about glyph map. So thanks for listening.
Thanks a lot for that, Sherry. Looks like we don't have any questions on the Slack. So I do have a question though. So is the package designed to be more used by, like, sort of what level of statistical competency do people who are intended to be using this package will they need to have?
So it's basically a tidy data workflow for spatial temporal data. So it's more intentionally for data analysis, where you have the data, and then if you don't want to spend a lot of time syncing between different tables, and then there's a data structure available that's out there for you to have a try.
Right. Okay. Yeah. And in terms of presenting, making the results sort of easily presentable to like wider audiences, is that is that much of an aim of the package as well?
So what do you mean by presents the results to a larger audience?
Like, let's say if people are, you know, if, I don't know, climate researchers or something are trying to present their results to, you know, maybe decision makers or politicians who may not have much statistical competency, is that much of a design feature to be able to?
Yeah, so it's a data structure, and then you can do all the data manipulations within the structure, and you can pipe it into the ggplot or other visualization package. There's also on the Kabul website there's the example where you can do interactive graphics with leaflets, with also Plotly. These are all the mediums that you can use to present it to other parties.
Cool. Okay. Well, thank you very much for that, Sherry. So I now introduce Adeniki Sorgan. She's a PhD student at the University of KwaZulu-Natal in South Africa, and also at the same time as a research fellow at the Centre for AIDS Program Research in South Africa. She's currently residing in Queensland, however, and today she's doing a 5-minute presentation discussing tools for predicting HIV viral load among HIV positive people. So I now hand over to Adeniki.
Thank you for having me. I'd like to thank all the committee for giving me this opportunity to share my research work. Can you all see my slide? Is it visible?
Yes, yeah.
Okay. Okay, so this is a methodology which I use in my research, and this work has been published. This work has been published in MDPR journal, and also as a book chapter in one of the HIV application book. So globally in 2021, 37 million adults over age 15 are living with HIV, and it is the leading cause of mortality and morbidity in sub-Saharan Africa, accounting for 71% of the global burden. And South Africa contributes approximately 22% of the global HIV burden, with an estimate of 7.8 million living with HIV. So the rural KwaZulu-Natal have the highest incidence rate of HIV. And according to the UNAIDS 95 targets, achieving HIV virus suppression is essential to reduce HIV transmission. And with a community viral load and predictors of unsuppressed viral load are valuable markers of sustained HIV. So application of spatial is important for us to be able to, oh, sorry, something is wrong with mine. Okay, if I just click that. Okay, I'm seeing different things, sorry. So the data, is an HIV incidence provision from the HIV incidence provision surveillance system data, which is a 2 cross-sectional survey and is a multi-state sampling design from a 2 small enumeration area. So questionnaire were obtained to were given to obtain the demographic, behavioral, and other form of information, and the blood sample were collected for HIV-related measure. So analysis of the descriptive were carried out in SAS, and an exploratory analysis was done using machine learning and correspondence analyses, and which I've also published this work in BMC research methodology, whereby we have a lot of covariates where we are able to identify potential factors from this analysis. And so we now went further to apply Bayesian geoadditive model using the INLA with a special effect and a nonlinear effect to find predictors of unsuppressed viral load in this community. And we use our software was used to for the analysis. So we accounted for another factor, nonlinear effect of covariates, and the spatial autocorrelation. Also, the shapefile was also developed in ArcGIS. So the outcome is dichotomized as being unsuppressed if the viral load is greater than or equal to 400 copies per mil, otherwise suppressed. And we have we diagnose 3 models, which is GAM, and then the structure additive model, which is the second model, which include the nonlinear effect of some covariates, and the unstructured additive model, which now includes the second model and the spatial effect. So the model with the smallest DIS was further built up on the Bayesian inference using the Gaussian Markov random field in the analysis. So descriptive statistics from this data, HIV prevalence is 40.2%, and we have a 46.1% of unsuppressed viral load from this data set. So the model diagnostics show that the unstructured model was the best fit model. And so this model was now further used to estimate the predictors from the Bayesian inference. So to test the significance of the individual predictors, we used the 95 credible interval, and this interval contains the number 0, which means that the parameter is not significant. So our result shows that the year of study, incomplete education, incomplete education, migration history, ever consume alcohol, no knowledge of HIV status, ever tested for TB and on TB medication are predictors of unsuppressed viral load in this community. Likewise, the nonlinear effect shows a positive nonlinear effect on age, the number of lifetime HIV status, lifetime tests, and household tests. And the log of having unsuppressed viral load decrease with age. It increases with higher number of household and increases with higher number of lifetime HIV tests. Also, we from the spatial effects, we're able to identify areas with higher risk of being unsuppressed, and which are the northwest and the northeast in this region. So, which we're able to inform, which we're able to show that having a predicted high-risk area, we have to be able to give an adequate attention to this area in terms of the HIV testing and better link to care and at initiation. And also we're able to show that the Bayesian approach is more beneficial in minimizing bias compared to classical approach, which many are research that have examined factors associated with unsuppressed viral loads I've used, and application of Bayesian is novel in this data set and also in establishing those predictors. So we were able to highlight all this area and then so that we were able to inform our stakeholders on how to intensify and link, HIV-related services to reduce community transmission, and also not accounting for spatial variability could result in skill results and also bias estimates, which can give a wrong conclusion and recommendation. So we're able to make a conclusion that's accounting for spatial heterogeneity and unobserved factor inherent within observation is crucial in informing and guiding for disease control strategies. And those identified high-risk areas will provide more opportunity to intensify efforts for sustainable HIV transmission reduction. I'd like to thank all the investigators of this work. Of course, the work has been funded by USAID, CDC, and a lot of collaborators. And also, a part of my work from this data set and this the model has been published, like I say, in a book chapter and also in a peer review publication. Thank you for having me.
Thank you very much. Very interesting. And please, if you have any questions for Adeniki, please put them in the thread in the main hall. And so I now introduce the next speaker. The next speaker is Ziyi Chi. Ziyi completed a master's in biostatistics at the University of Melbourne, which I believe was linked up with the Centre for Eye Research Australia, and is currently working as a clinical data analyst at Parexel in China. So Ziyi is going to give a 5-minute presentation on a tool developed in their masters to predict a general health utility score via a visual function questionnaire among patients with inherited retinal disease. So I now hand over to Ziyi.
Hello everyone, it's great to be here, and my name is Ziyi. Since the title is kind of long, let's get into the main theme. IRD condition is inherited retinal diseases. It's an eye condition that can cause severe vision loss or even blindness. It influences 1 in 4,000 people among Australians. So the research purpose is to address the knowledge gap in understanding the quality of life of IRD's populations, and also extrapolate global measures to assist plan for future gene therapy. The main objective of this research is to investigate the predicted value of the FQ25 and which of the items are most predictive of the EQ5D5L for the IRD's adult populations. Yes. So our candidates were pre-selected. They were self-enrolled through our online and telephone or even paper form options. But for this research purpose, we have our inclusion criteria, which is we only select people who give the consent and can have complete demographic information with complete questionnaires, and also who are adults with self-claimed IRD conditions. So in total, we have 639 out of 1,118 eligible participants. Sorry, it's getting yeah, in here. And as for our variable selection methods, we combined two types of methods. One is the penalized method, and the second is stepwise regression models. The stepwise regression, we use forward selections and backward eliminations. And for our penalized methods, we use the least absolute shrinkage and selection operators. In short, it's lasso. So basically, the penalized methods add constraints to the equation for having too many variables. Since our candidate variables is over 20, yes, it's over 20. We have over 20 questions. And then we split proportion into 50-50, and one for training and one for validation purpose. We also do the internal variable selections for our lasso group. And then we do the post estimations and compare the outcome and variable selections by the lasso groups as well as stepwise regression groups. All the analysis was done with data version 16. We have come up with two questions. The first, we have skewed outcome variables. It seems our participants, they were generally more optimistic towards their general health. And the second is we have missing values. Yes, especially like the driving related questions, because people with eye conditions, they don't normally drive due to the reason rather than their vision have due to the reason that they have the vision loss. So we only have 11 out of 12 subscales we included. And for our results, in here for our model transformations, we have our linear regression models, and then we have a squaring out count, and that model is the optimal model. So we use that. And then as for the outcome that's being selected, the last column is the variable selected by the stepwise methods, and the previous three were variables selected by the penalized methods. As we can see, there have similar prioritizations in terms of the variable selections. The first six were commonly selected by the whole methods. And in here, the adaptive lasso, it has the best performance out of all the methods. It can have around 51% of variance of the general health utility score can be predicted by our linear regression models. So all 6 subscales that were selected were general health, social functioning, dependency, role limitation, ocular pain, and distance visions. And so in conclude, lasso could be a useful tool on screening the key VFQ25 predictors for our general health utility score in our study, but there's no strong evidence. And also before the model is finalized, we need to consider to keep using the EQ5D to calculate the quality adjusted life year rather than trying to extrapolate from the VFQ25. Yeah, but there's still limitation and need to have further studies, such as we have selection bias need to be considered. And also we need to include health control as our reference in the futures. And also for acknowledge, great thanks to our conference for having this event, and also for my supervisor Myra and Fiona, and thanks Sarah for their fundings. Yeah, thank you.
Thank you very much, Ziyi, and again, please direct questions to her in the main hall. So I now hand over to the final speaker of this session, Gabriel Gonzalez. He's a reliability and maintenance specialist working towards a PhD in mechanical engineering at Curtin University, and also as a part-time engineer working in advanced process control at Andritz. Yes, and today he's going to do a 5-minute talk discussing, comparing two approaches for modeling the degradation of mining equipment. So I now hand over to Gabrielle.
Thank you, Alex, for that introduction. Do you hear me?
Yeah. Yes. Yeah.
Okay, cool. Yeah, I just today I want to take you into a side trip to a mining facility, and I want you to pretend to be a reliability engineer. As a reliability engineer, your main job is to make sure that your equipment is not going to fail, and also to schedule the routine maintenance in a costly effective way. So you assure that the equipment is going to be useful for a certain period of time, and you're not going to overspend money on that particular equipment. So now that we are wearing the hard hat of a reliability engineer, let's sit in the processing plant, and you are in charge of the mechanical integrity of one of these equipments, particularly the mill, for instance. And suddenly you receive a phone call from the planning superintendent throwing you a curveball. And he said, like, hey kid, what about pushing the mill maintenance 3 to 4 weeks? The spare parts are not here. Crews are hard to book these days. And you know how it is. So you, as a reliability engineer, you are naturally risk adverse. So you say, okay, let me look at the data and I'll come back to you later. Typically, these machines are inspected a couple of times during shutdowns or a couple of times a year even. So there's not much data around. So you do your best, you go to data, and this is what you got, like few data points, a no-go limit. And to be honest, like the current statistical tools that you can fit on these models are not the best. So your conclusion is basically very wide and not very accurate. The only thing you can say is that, okay, so I'm completely sure or almost certain that the machine is going to fail within the week 16 and the week 23, which gives a lot of room for the superintendent to make his mind. But the planning superintendent, he understood a completely different story, and he wants to delay the shutdown as much as she can. So, but you are completely against that because you know that your statistical tools are limited, and that is those boundaries, those uncertainty boundaries can be shorter, or they kind of hide the underlying truth, right? So so there is a conflict there. There is a dilemma that you need to solve. But the planning team, they kept going, and they told you, like, so typically your predictions are off. The last time we made it, the equipment lasts until the week 21, and most likely your measurements are also off, and so on and so forth. So you start thinking about all this issue, and you know what? Like they are not wrong. Most of our engineering methods do not account for this aspect. So what can we do? In the center, we went Bayesian. And why Bayesian? Because as a reliability engineers, we can take advantage of this unifying statistical framework that allow us to combine prior information, measurements, and mathematical knowledge of the degradation process. So it helps us to quantify uncertainty on one hand, and also provide mechanisms to reduce the uncertainty. In fact, out of my research, we have produced code and guidelines on how to use Bayesian hierarchical models in the context of noisy industrial datasets for two main classes of models: a stochastic process, in particular gamma and Wiener process, and also general path models or regression models. The future, and motivated by some really important work that is being published out there, we are trying to extend the stochastic Bayesian hierarchical models to incorporate covariate structure, because we know that there is a certain degradation pattern inside a pipeline or inside a grinding mill in this case. So we want to account for that in our model. And finally, we want to assess the cost of maintenance and the risk of failure implications of choosing one model over the other. So out of the Bayesian analysis, we have produced more information about the lifetime of individual equipment, otherwise unattainable by traditional approaches. This will help to support or contradict our reliability claim according to the shift of our posterior lifetime distribution or predicted posterior lifetime distribution, keeping us in the safe zone, or alternatively, allowing to leverage the opportunity of life extension that the planning superintendent was aiming for, all through the use of a principal mathematical approach. So what do you think? Do you think I should go Bayesian? Thank you very much.
Thank you very much, Gabriel. Very interesting to hear you know, an example of your research in the more industrial area. So that concludes session 8. And so I now hand back to the main organisers.
Thanks very much, Alex. That was great. And thanks for your talks. We're running a little bit behind, so we'll start again at 10 past the hour or 20 to the hour, depending on where you are. So we'll take a short break now and we'll see you shortly.